What was the first black hole? It's a question that carries us to the edge of time itself, to moments when the universe was so young that the very concepts of space and structure were still taking their first tentative steps toward existence. Welcome to a journey that takes us beyond the familiar realm of stars and galaxies, into the deepest wells of gravity that the universe has ever known. Tonight, we're exploring a question that pushes against the very boundaries of what we can observe and understand. As you settle into this moment of quiet contemplation, perhaps with the gentle weight of evening settling around you, consider the extraordinary fact that we can even ask such questions. Here we are, temporary arrangements of matter and energy, daring to probe the origins of the most extreme objects in the cosmos. Each of us under the same ancient sky that has witnessed every moment of cosmic history since light first broke free from the primordial darkness. The story we're about to explore challenges everything we typically think about beginnings and endings, about the relationship between matter and space-time itself. Before we had galaxies, before we had stars, before we had planets, or even the fundamental forces as we know them today, the seeds of the first black holes were already being planted in the fabric of reality. But these primordial monsters were unlike anything we observe in our modern universe. They were born not from the death of massive stars, but from the raw chaos of creation itself. Let's begin this gentle descent into the deepest mystery of cosmic evolution, where physics meets the limits of imagination, and where our most sophisticated theories dissolve into wonder and uncertainty. This is the story of the first black holes, told with the reverence it deserves and the curiosity that drives us to ask impossible questions about the nature of existence itself. The universe today is filled with black holes of staggering variety, stellar mass black holes, born from the violent collapse of massive stars, dot the cosmic landscape like invisible sentinels. Supermassive black holes, millions or billions of times the mass of our sun, lurk at the hearts of galaxies, orchestrating the dance of stars and gas across cosmic scales. And between these extremes, we find intermediate mass black holes, mysterious objects whose origins remain tantalizingly unclear. But none of these familiar categories can explain the very first black holes. To understand those primordial giants, we must journey back to a time when the universe itself was fundamentally different. A time when the rules we take for granted were still being written in the cosmic code. We must travel back to the earliest moments after the Big Bang, when the universe was a seething cauldron of energy and possibility. In those first fleeting moments, the universe was incredibly dense and hot, so dense that matter as we understand it couldn't exist. So hot that even atomic nuclei would be torn apart by the violent energy that filled every point in space. This was the era of cosmic inflation, when space itself expanded faster than the speed of light, stretching quantum fluctuations to macroscopic scales and setting the stage for everything that would follow. But hidden within this apparent chaos were the seeds of structure. Tiny variations in density, so small they were barely distinguishable from perfect uniformity, yet destined to grow under the patient influence of gravity into the cosmic web we observe today. These primordial fluctuations were like whispers in the cosmic wind, subtle hints of the magnificent architecture that would eventually emerge from the quantum foam. As the universe expanded and cooled, These density variations began their slow transformation into the first structures. In regions where matter was slightly more concentrated than average, gravity began its inexorable work of pulling more material inward. But this was not the gentle accumulation we might imagine. In the early universe, the physics of structure formation operated under conditions so extreme that the normal rules were stretched to their breaking point. The first black holes, those primordial monsters we seek to understand, emerged from this cosmic crucible through processes that remain at the very edge of our theoretical understanding. Unlike the stellar black holes that form from the collapse of massive stars, these ancient objects were born directly from the gravitational collapse of overdense regions in the early universe. They were the universe's first experiment with extreme gravity, its initial attempt to explore the deepest wells of space-time. Picture the early universe as a vast ocean of matter and radiation, rippling with waves of density that stretched across enormous scales. In the deepest troughs of these waves, where matter had accumulated in concentrations far beyond anything we see in the modern cosmos, gravity began to assert its dominance. As these regions continued to attract more material, they reached a critical threshold where nothing could prevent their complete gravitational collapse. But these primordial black holes were born in a universe that was still learning the rules of physics. The fundamental forces were still settling into their familiar roles. The very notion of stable matter was still experimental, and the relationship between energy and space-time was being negotiated through processes we can barely comprehend. In this alien environment, black holes could form through mechanisms that would be impossible in our current universe. Some of these first black holes might have been truly massive, containing the mass of millions or billions of suns, formed from the direct collapse of enormous gas clouds that had not yet fragmented into individual stars. Others might have been incredibly tiny by cosmic standards, microscopic black holes born from quantum fluctuations that were amplified by the extreme conditions of the early universe. These quantum black holes would have been smaller than atoms, yet containing more mass than mountains, representing the ultimate fusion of quantum mechanics and general relativity. The formation of these primordial giants would have been a spectacular process, though one that unfolded in a universe devoid of observers. As matter fell inward under its own gravity, it would have heated to temperatures that dwarf the cores of the most massive stars. The collapse would have generated gravitational waves that rippled through the fabric of space-time itself, carrying away energy and angular momentum as the forming black hole settled into its final state. But perhaps the most remarkable aspect of these first black holes is how they shaped the universe that followed. Unlike modern black holes, which exist in a cosmos already filled with structure and complexity, these primordial objects were pioneers, the first to explore the extreme physics of event horizons and singularities. They were the universe's initial foray into the realm where space and time become so curved that our normal understanding of reality breaks down completely. These ancient black holes served as gravitational seeds around which the first structures in the universe could form. Their immense gravitational pull attracted surrounding matter, creating the dense environments necessary for the first stars to ignite. In a very real sense, the first black holes were the architects of cosmic structure, the invisible hands that guided the transformation of a smooth, featureless universe into the rich tapestry of galaxies and stars we observe today. The physics governing the formation of these primordial objects pushes our theories to their absolute limits. We must consider not just the familiar effects of gravity and thermodynamics, but also the exotic physics of quantum fields in curved spacetime, the behavior of matter under conditions of extreme density and pressure, and the interplay between different fundamental forces in regimes where they may not yet have fully separated into their distinct identities. In those earliest epochs, the universe was governed by a unified physics that we can only dimly perceive through our current theories. The electromagnetic force, the weak nuclear force, and possibly even the strong nuclear force were unified with gravity in ways that fundamentally altered how matter and energy behaved. Under these conditions, the formation of black holes might have proceeded through channels that are completely closed off in our modern universe. The very concept of mass and energy was different in these primordial times. The matter that would eventually collapse into the first black holes existed in forms that have no analogue in our current cosmos. Exotic particles that decayed away billions of years ago. Energy densities that approach the fundamental scales where quantum gravity effects become dominant, and field configurations that could only exist in the unique conditions of the very early universe. As these primordial overdensities continued to grow under the influence of gravity, they reached a point of no return. The event horizon formed not as a distinct boundary, but as an inevitable consequence of space-time curvature becoming so extreme that even light could no longer escape. This was the birth of the first black hole, a moment when the universe first created a region of space so fundamentally altered that it became disconnected from the rest of reality. The formation of each primordial black hole was a cosmic phase transition, a moment when ordinary matter and energy cross the threshold into a realm governed by the most extreme physics imaginable. Inside the event horizon, the familiar laws of cause and effect break down. Time itself becomes meaningless, and space curves back on itself in ways that defy our deepest intuitions about the nature of reality. But what happened inside these first black holes remains one of the deepest mysteries in all of physics. Once matter crosses the event horizon, it enters a realm where our equations break down and our understanding dissolves into mathematical singularities. The very center of a black hole, where general relativity predicts infinite density and infinite curvature of space-time, represents a boundary beyond which even our most sophisticated theories cannot venture. These primordial black holes were not just passive gravitational wells. They were active participants in the cosmic drama, influencing their surroundings in ways that would echo through billions of years of subsequent evolution. As matter spiraled into these ancient monsters, it would have heated to incredible temperatures, creating the first quasars in a universe that had never before seen such brilliant beacons of light. These early active galactic nuclei would have outshone entire regions of space, their jets of superheated plasma extending across distances that dwarf our solar system. The feedback from these primordial giants would have been profound. Their gravitational influence would have stirred the surrounding medium, creating turbulence and shockwaves that either triggered or suppressed the formation of the first stars. Some regions would have been cleared of matter entirely, creating vast voids that would persist as cosmic deserts for billions of years. Other areas would have become stellar nurseries, dense with the raw materials needed for star formation, picture the early universe as a vast symphony, with these first black holes serving as the bass notes that give structure and rhythm to the entire composition. Their gravitational songs, played out over millions of years, would determine where matter accumulated and where it was expelled. They were the conductors of cosmic evolution, orchestrating the transformation of a simple, uniform cosmos into the complex web of structure we observe today. The diversity of these primordial black holes would have been staggering. Some formed from the direct collapse of massive gas clouds, creating supermassive objects that would eventually become the hearts of the largest galaxies. Others emerged from smaller overdensities, becoming the seeds of intermediate mass black holes that still puzzle astronomers today. And perhaps most intriguingly, some might have formed from quantum processes, creating microscopic black holes that existed at the intersection of general relativity and quantum mechanics. These quantum black holes represent a particularly fascinating chapter in the story of the first cosmic monsters. Born from fluctuations in the quantum vacuum itself, amplified by the extreme conditions of the early universe, they would have been objects of incredible density packed into volumes smaller than elementary particles. A single quantum black hole might have contained the mass of an asteroid compressed into a space smaller than a proton, creating gravitational fields so intense that they would warp space-time on scales we can barely imagine. The life and death of these quantum giants would have been dramatically different from their larger cousins. While massive black holes grow slowly by accreting matter and can persist for trillions of years, microscopic black holes would have been subject to Hawking radiation, the quantum process by which black holes slowly evaporate by emitting particles. The smallest of these primordial objects might have evaporated completely within the first seconds of cosmic history, their brief existence leaving only subtle traces in the cosmic microwave background radiation that bathes the universe today. But the evaporation of quantum black holes would not have been a quiet process. As these microscopic monsters shrank, their Hawking radiation would have become increasingly intense, eventually culminating in explosive bursts of energy that would have briefly outshone entire stellar clusters. These primordial explosions would have created exotic particles and high-energy radiation, seeding the early universe with elements and energy that would influence the formation of the first stars and galaxies. The detection of these ancient objects presents one of the greatest challenges in modern astronomy. Unlike stellar black holes, which we can observe through their gravitational effects on nearby stars, or supermassive black holes, which reveal themselves through their brilliant accretion disks, primordial black holes are nearly impossible to observe directly. They exist as invisible gravitational ghosts, their presence detectable only through subtle effects on their surroundings. Some astronomers believe that primordial black holes might comprise a significant fraction of the mysterious dark matter that dominates our universe. These ancient objects, formed in the first moments after the Big Bang, could be scattered throughout the cosmos as invisible components of galactic halos and cosmic structure. If this hypothesis is correct, then the first black holes are not merely historical curiosities, but active participants in the modern universe, their gravitational influence shaping the orbits of stars and the distribution of matter on the largest scales. The search for primordial black holes has led astronomers to develop increasingly sophisticated observational techniques. Gravitational microlensing experiments scan the sky looking for the brief brightening of background stars that occurs when a compact object passes in front of them. Gravitational wave detectors listen for the characteristic chirps produced when two black holes spiral into each other and merge, hoping to catch the signatures of primordial objects formed in the early universe. Recent discoveries have added new chapters to the story of these ancient monsters. The detection of gravitational waves from merging black holes has revealed a population of objects with masses that are difficult to explain through stellar evolution alone. Some of these might be primordial black holes, formed not from the death of massive stars, but from the direct collapse of overdense regions in the early universe. The cosmic microwave background, that faint afterglow of the Big Bang that permeates all of space, carries subtle imprints of the first black holes. Tiny variations in temperature and polarization encode information about the density fluctuations that gave birth to these primordial monsters. By carefully analyzing these ancient photons, astronomers are beginning to reconstruct the conditions that existed in the first moments after the Big Bang, when the seeds of the first black holes were planted in the quantum foam of creation. But perhaps the most profound aspect of studying the first black holes is what they reveal about the nature of gravity itself. These objects represent the ultimate test of Einstein's general relativity, pushing the theory into regimes of extreme curvature and density where quantum effects become impossible to ignore. The formation and evolution of primordial black holes occurs at the boundary between classical and quantum physics, in a realm where our current theories begin to break down and new physics might emerge. The first black holes were born in a universe that was still learning the rules of existence, still experimenting with the fundamental forces and particles that would define reality for billions of years to come. They emerged from conditions so extreme that matter, energy, space, and time itself existed in forms that have no analog in our modern cosmos. Yet these ancient objects managed to survive the cosmic transitions that followed, persisting as gravitational fossils from the dawn of time. As we continue our gentle journey through this cosmic mystery, we find ourselves confronting questions that touch the very foundations of physics. How does matter behave under conditions of infinite density? What happens to information that falls into a black hole? How do quantum mechanics and general relativity merge in the extreme environment near a singularity? The first black holes, those primordial monsters born from the chaos of creation, hold the keys to these profound mysteries. Tonight, as you drift deeper into contemplation of these cosmic giants, remember that you are connected to their ancient story. The atoms in your body were forged in stellar cores, but the very existence of those stars depended on the gravitational influence of primordial black holes. The calcium in your bones, the iron in your blood, the oxygen you breathe, all owe their existence to cosmic processes that were set in motion by these invisible architects of structure. The first black holes were more than just extreme gravitational objects. They were the universe's first attempt to explore the deepest mysteries of existence, to push the boundaries of what matter and energy could become under the influence of gravity's relentless pull. In their formation, the cosmos took its first steps toward understanding its own capacity for creating the impossible, for birthing objects so extreme that they challenge our most fundamental assumptions about the nature of reality itself. These primordial giants existed in a universe that was fundamentally different from our own, in ways that challenge our deepest intuitions about reality. The cosmic environment of those earliest epochs was so alien, so removed from anything we can directly experience, that even our most sophisticated simulations can only approximate the conditions that gave birth to the first black holes. The very fabric of space-time itself was different then, woven from quantum threads that vibrated with energies approaching the Planck scale, where the distinction between matter and geometry begins to dissolve. In those ancient times, the universe was a seething ocean of relativistic plasma, where particles and antiparticles danced in and out of existence with such frequency that the vacuum itself pulsed with creative potential. The temperature was so extreme that even the most stable forms of matter we know today would have been instantly vaporized, existing only as fleeting patterns in the quantum foam that filled every point in space. Yet within this apparent chaos, the seeds of order were already taking root. The formation of the first black holes occurred during what cosmologists call the radiation-dominated era, when photons carried more energy than matter itself. In this photon-rich environment, the usual mechanisms of gravitational collapse operated under radically different rules. Radiation pressure, which today plays only a minor role in stellar physics, was then a dominant force that could either aid or hinder the formation of dense structures. The interplay between matter, radiation, and gravity created a delicate balance that determined which primordial overdensities would collapse into black holes and which would disperse back into the cosmic medium. But perhaps most remarkably, these early black holes formed in a universe where the fundamental constants of physics may have been different from their present values. The strength of gravity, the mass of elementary particles, even the speed of light itself might have evolved as the cosmos expanded and cooled. Under these shifting conditions, the critical mass required for black hole formation could have been dramatically different from what we calculate using modern physics. Objects that would be stable today might have collapsed catastrophically in the early universe, while structures that seem impossibly massive might have formed with ease. The gravitational collapse that created these primordial monsters was not the relatively slow process we observe in stellar death today. In the dense, hot environment of the early universe, collapse could occur on timescales measured in microseconds rather than millennia. As matter fell inward at nearly the speed of light, it would have generated shock waves that propagated through the surrounding medium, creating ripples of compression and rarefaction that influence structure formation across vast distances. These collapsing regions would have become cosmic laboratories where the most extreme physics played out on scales both vast and infinitesimal. As matter approached the forming event horizon, time dilation effects would have become so severe that external observers would have seen the collapse freeze at the critical moment, while infalling material experienced the formation of the singularity in proper time. This fundamental asymmetry in the perception of time near black holes would have created causal disconnections in the early universe, regions where events unfolded according to different temporal rhythms. The diversity of formation mechanisms available in the primordial universe staggers the imagination. Direct collapse of massive gas clouds could create supermassive black holes without the need for an intermediate stellar phase. Cosmic string loops, those hypothetical one-dimensional defects in space-time predicted by some theories of the early universe, could have collapsed to form black holes of intermediate mass. Phase transitions in exotic matter fields could have triggered localized regions of gravitational instability, spawning populations of black holes with characteristic masses determined by the underlying particle physics. Perhaps most intriguingly, the early universe might have been populated by black holes formed through purely quantum processes. In the extreme conditions near the Planck epoch, when the universe was less than a trillionth of a trillionth of a trillionth of a second old, quantum fluctuations could have been so intense that they spontaneously created closed trapped surfaces in space-time itself. These quantum black holes would have emerged directly from the foam of virtual particles and fields that define the vacuum at the deepest level, representing the ultimate fusion of general relativity and quantum mechanics. The environment surrounding these nascent black holes would have been unlike anything we can observe in the modern universe. The accretion of matter onto a primordial black hole would have occurred in a medium dominated by radiation, rather than the relatively cold gas and dust we see today. As material spiraled inward, it would have been heated not just by gravitational compression, but by the intense radiation field that filled all of space. The resulting accretion disks would have been blazingly hot, emitting high-energy photons that could ionize matter across vast distances. These early quasars, powered by primordial supermassive black holes, would have been among the first sources of light in the cosmic dark age. Their brilliant emission would have begun the process of reionization, stripping electrons from hydrogen atoms and transforming the neutral gas that filled the universe back into a plasma state. This cosmic phase transition would have had profound consequences for subsequent structure formation, creating feedback loops between black hole growth and the formation of the first stars and galaxies. But the influence of primordial black holes extended far beyond their immediate surroundings. Their gravitational fields would have acted as cosmic magnifying glasses, focusing and amplifying the subtle density fluctuations that would eventually grow into galaxies and clusters. The presence of these massive objects would have created gravitational potential wells that attracted surrounding matter, accelerating the formation of structure in their vicinity, while creating vast, empty regions elsewhere. The merger of primordial black holes would have been spectacular events that shaped the early cosmos in ways we are only beginning to understand. When two of these massive objects spiraled into each other, they would have generated gravitational waves of unprecedented amplitude, ripples in space-time so powerful that they would have influenced the formation of structure across enormous distances. These primordial gravitational wave backgrounds might still be detectable today as subtle signatures in the cosmic microwave background radiation, or in the data from our most sensitive gravitational wave observatories. The evolution of these ancient black holes was governed by physics that operated at the intersection of general relativity, quantum field theory, and cosmology. As the universe expanded and cooled, the environment around these objects changed dramatically, altering their growth rates and the mechanisms by which they interacted with their surroundings. Black holes that were actively accreting in the early universe might have become quiescent as the surrounding medium was swept away by cosmic expansion, while others might have experienced episodes of renewed growth as they encountered dense clouds of dark matter or primordial gas. The feedback between black hole growth and cosmic evolution created the large-scale structure of the universe, where a complex web of cause and effect that determine observe today. Regions where primordial black holes formed early and grew rapidly became the sites of massive galaxy clusters, while areas where black hole formation was suppressed remained as cosmic voids. This co-evolution of black holes and cosmic structure represents one of the most profound examples of how local physics can influence global properties of the universe. Recent theoretical work has suggested that some primordial black holes might have been born spinning at nearly their maximum possible rate, approaching the theoretical limit set by general relativity. These rapidly rotating objects would have possessed ergospheres, regions outside the event horizon, where space-time itself is dragged around by the black hole's rotation. Matter falling into these ergospheres could have been accelerated to incredible velocities, creating jets of relativistic particles that extended across cosmic distances and influenced structure formation far from their source. The quantum properties of primordial black holes present some of the deepest puzzles in theoretical physics. According to quantum mechanics, black holes should evaporate through Hawking radiation, slowly losing mass as they emit particles into the surrounding space. For the smallest primordial black holes, this evaporation process would have been rapid and violent, culminating in explosive bursts of energy that could have briefly outshone entire galaxies. These primordial fireworks would have enriched the early universe with exotic particles and high-energy radiation, potentially influencing the formation of the first complex structures. The information paradox associated with black hole evaporation takes on special significance for primordial objects. If these ancient black holes have indeed evaporated completely, what happened to the information they contained about the early universe? This question touches the foundations of quantum mechanics and general relativity, forcing us to confront the possibility that information about the earliest moments of cosmic history might be forever lost, encoded in correlations too subtle for us to detect. The search for surviving primordial black holes has become one of the most active areas of modern astrophysics. These ancient objects might reveal themselves through their gravitational effects on nearby matter, their role as lenses that magnify background sources, or their contribution to the mysterious dark matter that dominates cosmic structure. Some researchers have proposed that the dark matter itself might consist partially or entirely of primordial black holes, invisible remnants of the universe's violent birth that continue to shape cosmic evolution through their gravitational influence alone. The formation of the first black holes marked a fundamental transition in cosmic history, the moment when gravity first succeeded in creating objects so dense that they disconnected themselves from the rest of space-time. These primordial monsters were the universe's first successful experiments with extreme curvature, its initial exploration of the regime where classical physics gives way to quantum gravity effects. In their dark hearts, the familiar concepts of space and time break down completely, replaced by something far stranger and more fundamental. As we continue our gentle descent into this cosmic mystery, we find ourselves confronting the deepest questions about the nature of reality itself. The first black holes were not merely extreme gravitational objects, but windows into the most fundamental properties of space-time, matter, and information. They emerged from the quantum foam of creation as the universe's first attempt to understand its own capacity for creating the impossible, for birthing regions of space so curved that they become causally disconnected from everything else that exists. Tonight, as you drift deeper into contemplation of these ancient giants, remember that their story is intimately connected to your own existence. The elements that compose your body, the forces that bind your atoms together, even the structure of the galaxy that contains our solar system, all bear the subtle fingerprints of these primordial architects. In understanding the first black holes, we glimpse not just the violent birth of cosmic monsters, but the delicate processes that shaped a universe capable of supporting the complexity and beauty we observe today. The story of these primordial giants becomes even more extraordinary when we consider how they shape itself in the early universe. As the first, the very notion of time, black holes formed, they created regions where time flowed at dramatically different rates compared to the surrounding cosmos. Near the event horizons of these massive objects, time would crawl to an almost complete standstill from the perspective of distant observers, while the interior regions experienced temporal flow in ways that our mathematics can describe, but our minds struggle to comprehend. This temporal distortion had profound consequences for the evolution of the early universe. Imagine vast regions of space where cosmic evolution proceeded at different rates, where some areas aged billions of years while others experienced only moments. The gravitational time dilation around primordial black holes created a patchwork of temporal zones, each evolving according to its own internal clock, yet all connected by the inexorable expansion of space itself. The matter that fell into these ancient monsters carried with it the memory of the universe's birth. Every particle that crossed an event horizon bore information about the conditions that existed in those first crucial moments after the Big Bang. In a sense, primordial black holes became cosmic archives, storing within their dark hearts the secrets of creation itself. Yet this information was trapped beyond any possibility of retrieval, hidden behind horizons that no signal could ever cross. But perhaps the most remarkable aspect of these early black holes was how they began to teach the universe about its own fundamental limits. Through their formation and evolution, the cosmos first explored the boundary between the quantum and classical realms, the edge where general relativity meets quantum mechanics in a dance of mathematical beauty and physical extremity. Each primordial black hole was a natural laboratory where the most fundamental questions about reality were being answered through pure gravitational physics. The accretion processes around these ancient objects operated under conditions that have no parallel in our modern universe. In the dense, radiation-dominated environment of the early cosmos, matter falling onto primordial black holes would have been subjected to forces that stretched the very definition of physical possibility. Temperatures soared to levels where the distinction between matter and energy became meaningless, where particles existed in states of such high excitation that they challenged our understanding of quantum field theory itself. These extreme accretion environments would have produced the first magnetic fields of cosmic significance. As ionized matter spiraled inward, it would have generated powerful magnetic dynamos that twisted and amplified field lines into configurations of breathtaking complexity. These primordial magnetic fields would have extended far beyond the black holes themselves, threading through the surrounding medium and influencing the formation of structure across enormous distances. The jets produced by rapidly spinning primordial black holes would have been among the most powerful phenomena in the early universe. These collimated streams of relativistic particles would have carved through the surrounding medium like cosmic blowtorches, creating cavities and shock fronts that influence the distribution of matter across scales, ranging from individual protogalaxies to entire clusters. The energy deposited by these jets would have heated vast regions of space, preventing the formation of structure in some areas while triggering it in others. As the universe continued to expand and cool, The environment around primordial black holes underwent dramatic changes that fundamentally altered their growth patterns and observational signatures. The transition from a radiation-dominated to a matter-dominated cosmos marked a crucial turning point in black hole evolution. Suddenly, the pressure support that had prevented many structures from collapsing was removed, allowing matter to fall more readily into gravitational potential wells. This cosmic phase transition created conditions that were ideal for rapid black hole growth. Primordial objects that had been relatively quiet during the radiation era suddenly found themselves surrounded by vast reservoirs of matter that could be efficiently accreted. Some black holes experienced exponential growth phases that increased their masses by factors of millions or billions in cosmologically short periods. These rapidly growing objects became the seeds of the supermassive black holes we observe at the centers of galaxies today. But not all primordial black holes experience such dramatic growth. Many found themselves in regions where matter was swept away by cosmic expansion or blown out by the energetic feedback from nearby sources. These objects became gravitational fossils, retaining the masses they acquired during their initial formation while the universe evolved around them. Today, these ancient relics might exist as intermediate mass black holes scattered throughout galactic halos and cosmic voids, invisible reminders of the universe's violent youth. The quantum properties of the smallest primordial black holes present some of the most profound puzzles in modern physics. According to our current understanding, black holes with masses below a certain threshold should evaporate completely through Hawking radiation within the age of the universe. This means that any quantum black holes formed in the earliest moments after the Big Bang should have disappeared long ago, leaving behind only subtle traces of their existence. Yet the evaporation of these microscopic monsters would not have been a quiet process. As they shrank, their surface temperatures would have increased dramatically, eventually reaching levels where they emitted not just ordinary particles but exotic forms of matter that have no stable existence in our current universe. The final moments of a quantum black hole's life would have been spectacular, releasing energies equivalent to millions of hydrogen bombs in bursts lasting mere microseconds. These primordial explosions would have created some of the most extreme conditions ever achieved in nature. For brief instance, tiny volumes of space would have contained energy densities approaching those that existed in the first moments after the Big Bang itself. The particles produced in these explosions would have included exotic species that decay almost immediately, leaving behind cascades of secondary radiation that could have influenced the formation of the first complex structures. The detection of these evaporation signatures represents one of the holy grails of modern astrophysics. If we could identify the characteristic spectral features of primordial black hole evaporation in the cosmic microwave background or in high-energy gamma-ray observations, it would provide direct evidence for the existence of these ancient objects and invaluable insights into the physics of the early universe. The gravitational waves produced by merging primordial black holes would have created a background of space-time ripples that might still be detectable today. Unlike the gravitational waves from stellar mass black hole mergers that we observe with current detectors, the signals from primordial objects would have been redshifted by cosmic expansion into frequency ranges that require different observational strategies. Future space-based gravitational wave observatories might be able to detect these ancient echoes, providing a new window into the earliest epochs of cosmic history. The formation of primordial black holes also had profound implications for the development of cosmic structure on the largest scales. Their gravitational influence would have created preferred directions for matter flow, establishing filaments and voids that characterizes the foundation for the cosmic web of universe today. The interplay between black hole formation, dark matter clustering, and baryon physics created a complex feedback system that determined which regions of space would become dense nodes of structure and which would remain as cosmic deserts. Some theoretical models suggest that primordial black holes might have played a crucial role in solving one of cosmology's greatest puzzles: the origin of supermassive black holes in the early universe. Observations of quasars at very high redshifts reveal the existence of black holes containing billions of solar masses when the universe was less than 1 billion years old. The formation of such massive objects through conventional stellar evolution seems impossible given the limited time available, but primordial black holes could have provided the necessary head start. These supermassive primordial objects would have been born with masses already approaching those of entire star clusters, giving them a tremendous advantage in the cosmic race to build galactic nuclei. Their early formation would have allowed them to begin accreting matter immediately, without waiting for the first stars to form and evolve. This head start could explain how supermassive black holes managed to assemble so quickly in the young universe. The chemical enrichment patterns around primordial black holes would have been stellar mass objects today. In dramatically different from those we observe around the metal-free environment of the early universe, accretion onto black holes would have produced unique signatures in the surrounding medium. The high-energy radiation from these ancient quasars would have triggered nuclear reactions in the pristine hydrogen and helium gas, creating the first heavy elements through processes that have no modern analog. These primordial enrichment processes would have created chemical gradients that influenced the formation of the first stars and galaxies. Regions that were exposed to radiation from early quasars would have developed different chemical compositions than areas that remained in the cosmic dark, leading to distinct populations of stellar objects with characteristic abundance patterns that might still be observable in the oldest stars in our galaxy. The feedback mechanisms associated with primordial black hole growth created some of the most complex astrophysical phenomena ever to exist in our universe. The interplay between accretion, jet formation, radiation pressure, and gravitational effects produced systems of stunning complexity that operated on scales ranging from the microscopic to the truly cosmic. These feedback loops determine not only the growth rates of individual black holes, but also the large-scale distribution of matter and energy throughout the universe. As we drift deeper into this cosmic mystery, we begin to appreciate how the first black holes served as cosmic architects, shaping not just the distribution of matter, but the very laws of physics as they played out across space and time. These ancient objects were the universe's first successful experiments with extreme gravity, its initial attempts to explore the deepest wells of space-time curvature, where the familiar concepts of past and future begin to lose their meaning. The legacy of these primordial monsters extends far beyond their direct gravitational effects. They taught the universe fundamental lessons about the relationship between matter, energy, space, and time that continue to influence cosmic evolution today. Every galaxy, Every star, every planet that formed in the billions of years that followed bears some trace of their ancient influence, carrying forward the memory of that first encounter between matter and the most extreme physics imaginable. Tonight, as you contemplate these cosmic giants from the dawn of time, remember that you are connected to their story in ways both profound and personal. The very atoms that compose your body were shaped by processes that trace their origins back to these primordial architects. The forces that bind your cells together, the energy that powers your thoughts, even the structure of space-time around you all bear the subtle fingerprints of those first black holes that dared to explore the deepest mysteries of existence itself. The question of what constitutes the very first black hole becomes even more tantalizing when we consider the possibility that these primordial giants might not have formed through any process we can directly observe or replicate in our modern universe. The conditions that existed in those earliest epochs were so fundamentally different from anything we experience today that the very mechanisms of black hole formation operated according to rules that challenge our deepest understanding of physics itself. Picture the universe when it was less than a second old, a seething cauldron of exotic particles and fields that have long since decayed into the familiar matter we know today. In this alien environment, the distinction between matter and energy was fluid, constantly shifting as the cosmos underwent phase transitions that transformed the very nature of reality. Particles with masses trillions of times greater than anything we can create in our most powerful accelerators danced through space for brief moments before decaying into cascades of lighter particles. These massive primordial particles, if they existed, would have created gravitational disturbances unlike anything possible in our current universe. When they decayed, they would have released enormous amounts of energy in highly localized regions, potentially creating the seeds for black hole formation through mechanisms that have no modern analog. The gravitational fields generated by these exotic matter configurations could have reached critical densities without requiring the slow accumulation of ordinary matter that characterizes stellar collapse today. The very fabric of space-time itself was different in those ancient moments. Quantum fluctuations that are negligible in our expanded, cooled universe could have been amplified to macroscopic scales by the extreme curvature that existed everywhere in space. These fluctuations might have created closed trapped surfaces spontaneously, forming black holes directly from the geometry of space-time itself, rather than from the collapse of matter. In this scenario, the first black holes would have been born from pure geometry, crystallizations of curvature that emerged from the quantum foam of creation. The temperature of the early universe was so extreme that even the vacuum itself was unstable, constantly boiling with virtual particles that borrowed enormous amounts of energy for infinitesimally brief periods. Under these conditions, the boundary between virtual and real particles became blurred, allowing quantum effects to influence the formation of structure in ways that are impossible today. Some theoretical models suggest that these quantum processes could have created black holes with masses spanning an incredible range, from microscopic objects smaller than elementary particles to supermassive giants containing billions of times the mass of our Sun. The formation of these quantum black holes would have been instantaneous events, occurring on timescales so brief that the very concept of duration becomes meaningless. Unlike the gradual collapse we observe in stellar death today, which unfolds over thousands of years, primordial black hole formation could have happened in less time than it takes light to cross the nucleus of an atom. These were not slow gravitational collapses, but sudden crystallizations of space-time geometry, moments when the universe discovered new ways to fold space and time back upon themselves. But perhaps the most extraordinary aspect of these primordial formations was how they occurred in a universe that was still learning the rules of causality itself. The light cones that define the causal structure of space-time were constantly shifting as the universe expanded and the fundamental forces separated from their unified state. In this fluid causal environment, black holes could form through processes that violated our normal understanding of cause and effect, emerging from configurations of matter and energy that seem to violate the very logic of temporal sequence. The diversity of formation mechanisms available in the primordial universe created a zoo of black hole types that defies our current classification schemes. Some emerge from the collapse of cosmic strings, one-dimensional defects in space-time that stretched across enormous distances. Others formed at the intersections of domain walls, two-dimensional surfaces where different regions of space had settled into different vacuum states. Still others might have crystallized around magnetic monopoles, exotic particles predicted by some theories but never observed in nature. Each of these formation pathways would have created black holes with distinctive properties that reflected their exotic origins. String-born black holes might have retained some memory of their one-dimensional ancestry, exhibiting gravitational fields with subtle asymmetries that distinguish them from spherically symmetric objects. Black holes formed from domain wall collisions could have been born with intrinsic angular momentum patterns that defied our usual understanding of rotation in curved space-time. The magnetic monopole black holes present a particularly fascinating possibility. If these exotic particles existed in the early universe, they would have carried magnetic charges that had no electric analog, creating gravitational objects with electromagnetic properties unlike anything we observe today. The event horizons of such black holes would have been threaded with magnetic field lines of incredible intensity, creating conditions where the boundary between electromagnetic and gravitational physics dissolved entirely. The environment surrounding these nascent black holes would have been a playground for the most extreme physics imaginable. The intense gravitational fields would have created regions where space and time became so distorted that particles could tunnel between different epochs, where energy could flow backward through time, and where the very notion of locality broke down completely. These were cosmic laboratories where the universe experimented with physical processes that pushed the boundaries of mathematical possibility. As matter fell into these primordial monsters, it would have encountered conditions that transformed the very meaning of existence. The approach to the event horizon would have been a journey through increasingly exotic states of matter and energy, where familiar particles were stretched and twisted by tidal forces into configurations that challenged the fundamental principles of quantum mechanics. The information carried by this infalling matter would have been encoded in the black hole's internal structure in ways that remain one of the deepest mysteries in theoretical physics. The interior regions of these ancient black holes present puzzles that stretch our understanding to its absolute limits. Beyond the event horizon, where classical general relativity predicts the existence of singularities with infinite density and curvature, the true physics remains completely unknown. Some theories suggest that quantum effects might prevent the formation of true singularities, replacing them with exotic structures where space and time take on forms that have no analog in our familiar four-dimensional reality. The possibility that primordial black holes contain wormhole connections to other regions of space-time has captivated theoretical physicists for decades. If such connections exist, they would create a hidden network of gravitational shortcuts threading through the universe, allowing information, and perhaps even matter, to travel between distant regions through paths that bypass ordinary space. These cosmic highways would be invisible to external observers, but might play crucial roles in determining the large-scale structure of the universe. The quantum mechanical properties of primordial black holes operate in regimes where our current theories reach their limits of applicability. The Hawking radiation emitted by these objects would have carried information about the quantum states of matter under conditions of extreme curvature, providing insights into the fundamental nature of information itself. The entanglement patterns between particles inside and outside the event horizon would have created correlations that stretched across cosmic distances, binding together regions of space that appeared to be completely disconnected. These quantum correlations might have served as the seeds for the cosmic web of structure we observe today. The entanglement between particles that fell into primordial black holes and those that remained in the surrounding medium could have created preferred directions for matter flow, establishing the filamentary patterns that characterize the distribution of galaxies on the largest scales. In this view, the cosmic web itself is a manifestation of quantum entanglement on cosmological scales, a vast network of correlations that trace their origins back to the formation of the first black holes. The evolution of these primordial objects as the universe expanded and cooled presents challenges that push the boundaries of our theoretical understanding. As the cosmic background temperature dropped below the Hawking temperature of the smallest black holes, these objects would have begun to evaporate rapidly, releasing their stored mass energy back into the surrounding medium. The particles produced in this evaporation process would have included exotic species that existed nowhere else in the universe, creating brief moments when the cosmos was populated by matter configurations of stunning complexity. The larger primordial black holes would have experienced a different fate, growing slowly through the accretion of surrounding matter while the universe evolved around them. These ancient objects would have served as gravitational anchors around which the first structures formed, their steady growth providing the mass concentrations necessary to overcome the expansion of space and begin the process of cosmic structure formation. The feedback between primordial black hole growth and the formation of the first stars created complex evolutionary pathways that determined the chemical and dynamical properties of early galaxies. Regions where black holes formed early and began accreting efficiently would have been heated by the resulting radiation, preventing the formation of small-scale structure while promoting the assembly of more massive objects. Other areas where black hole formation was delayed or suppressed would have evolved along different tracks, creating the diversity of galactic types we observe today. The gravitational wave signatures of primordial black hole mergers would have created a stochastic background of space-time ripples that might still be detectable by future observational campaigns. Unlike the discrete signals from individual merger events that current detectors observe, this primordial gravitational wave background would appear as a smooth enhancement in the noise floor across a wide range of frequencies. The detection of such a background would provide direct evidence for the existence of primordial black holes and valuable constraints on the physics of the very early universe. The search for these ancient gravitational wave echoes represents one of the most ambitious observational programs in modern astrophysics. Space-based interferometers capable of detecting millihertz gravitational waves might be sensitive enough to detect the redshifted signals from primordial black hole mergers that occurred when the universe was still in its infancy. These observations would open a new window into the earliest epochs of cosmic history, allowing us to probe conditions that existed long before the formation of the first stars and galaxies. The connection between primordial black holes and the mysterious dark matter that dominates cosmic structure remains one of the most intriguing possibilities in modern cosmology. If a significant fraction of dark matter consists of primordial black holes, these ancient objects would be scattered throughout galactic halos as invisible gravitational fossils from the universe's violent birth. Their gravitational effects would influence the orbits of stars and the distribution of visible matter in ways that might be detectable through careful observational studies. The mass spectrum of primordial black holes could encode information about the physics of inflation and the nature of the fields that drove cosmic expansion in the earliest moments. Different inflationary models predict characteristic patterns in the primordial density fluctuations that would translate into specific distributions of black hole masses. By studying the population of surviving primordial black holes, astronomers might be able to distinguish between different theories of the universe's birth and evolution. Recent advances in gravitational lensing surveys have begun to probe the population of compact objects in our galaxy with unprecedented sensitivity. These observations search for the characteristic signatures of gravitational microlensing that occur when a compact object passes in front of a background star, temporarily magnifying its apparent brightness. If primordial black holes comprise a significant fraction of the dark matter in our galactic halo, they should produce detectable microlensing events at a rate that depends on their mass distribution and spatial clustering properties. The theoretical framework for understanding primordial black hole formation continues to evolve as new insights emerge from the intersection of cosmology, particle physics, and general relativity. Advanced numerical simulations that incorporate the full complexity of the early universe's physics are beginning to reveal the intricate processes that determined which primordial overdensities collapsed to form black holes and which dispersed back into the cosmic medium. These simulations must account for the effects of radiation pressure, magnetic fields, turbulence, and exotic matter interactions under conditions that have no modern analogue. As we continue our gentle exploration of these cosmic mysteries, we find ourselves drawn deeper into questions that touch the very foundations of physical reality. The first black holes emerged from a universe so fundamentally different from our own that they serve as windows into realms of physics that remain largely unexplored. They were born in an epoch when the familiar laws of nature were still crystallizing from more fundamental principles, when space and time themselves were learning the rules that would govern their behavior for billions of years to come. Tonight, as you drift toward the edge of sleep, carried by the rhythm of your own breathing, remember that you are part of a story that began with these ancient gravitational giants. The matter that composes your body, the forces that hold your atoms together, even the structure of the galaxy that contains our solar system, all bear the invisible influence of those primordial architects. In their dark hearts, the universe first learned to create regions of space so extreme that they transcended the ordinary flow of cause and effect, becoming timeless vaults where the secrets of creation remain forever locked away. The question of what was the first black hole may ultimately lead us not to a single answer, but to a recognition that the universe's capacity for creating the extraordinary began in its very first moments. These primordial monsters were not merely gravitational anomalies, but cosmic pioneers, the first objects to explore the deepest mysteries of existence and to push the boundaries of what matter, energy, space, and time could become under the influence of gravity's relentless embrace. But the story of primordial black holes reveals an even deeper mystery when we consider how these ancient objects might have influenced the very structure of reality itself. As the universe expanded and evolved, these gravitational titans didn't simply grow larger or fade away. They became active participants in shaping the cosmic environment around them, creating conditions that would determine the fate of matter and energy for billions of years to come. The accretion disks that formed around the most massive primordial black holes operated under physical conditions that pushed the boundaries of theoretical understanding. In the dense, hot environment of the early universe, matter spiraling into these objects would have been subjected to magnetic fields of unprecedented strength, twisted into helical configurations that defied the familiar physics of stellar accretion. These primordial dynamos generated field lines that extended across cosmic distances, threading through the surrounding medium like invisible highways that guided the flow of charged particles. The jets launched by rapidly spinning primordial black holes would have been among the most powerful phenomena ever to exist in our universe. Unlike the relatively modest outflows we observe from stellar mass black holes today, these ancient jets carried energies equivalent to the total luminosity of entire galaxy clusters. They carved through the primordial medium like cosmic blowtorches, creating cavities and shock fronts that influenced the distribution of matter across scales that dwarfed individual protogalaxies. But perhaps most remarkably, these jets operated in a universe where the very concept of empty space was fundamentally different. The quantum vacuum of the early cosmos was filled with exotic particles and fields that have long since decayed, creating interactions between jet material and the surrounding medium that have no modern analog. The resulting shock structures would have exhibited properties that challenged our understanding of plasma physics, creating conditions where ordinary matter was transformed into states of organization that existed nowhere else in the universe. The gravitational lensing effects of primordial black holes would have created the first cosmic magnifying glasses, focusing and amplifying the faint signals from the earliest sources of electromagnetic radiation. These ancient lenses would have been far more powerful than anything we observe today, capable of magnifying background sources by factors of millions or billions. The caustic patterns created by these gravitational focusing effects would have produced networks of enhanced radiation that influenced the thermal evolution of surrounding gas clouds. As the universe transitioned from its radiation-dominated phase to matter domination, the environment around primordial black holes underwent dramatic changes that fundamentally altered their evolutionary pathways. The sudden removal of radiation pressure support allowed matter to fall more freely into gravitational potential wells, triggering episodes of rapid accretion that could increase black hole masses by enormous factors in cosmologically brief periods. These growth spurts were not uniform processes, but occurred in chaotic bursts driven by the complex interplay between accretion physics and feedback effects. As matter fell inward, it would heat to temperatures where nuclear reactions became possible, creating the first heavy elements in the universe through processes that occurred not in stellar cores, but in the swirling maelstrom surrounding black hole event horizons. The resulting abundance patterns would have been unlike anything we observe in modern stellar populations, carrying unique signatures that might still be detectable in the oldest stars in our galaxy. The magnetic field configurations around accreting primordial black holes created some of the most complex electromagnetic phenomena ever to exist in nature. Field lines that connected the black hole's ergosphere to distant regions of space could channel energy and angular momentum across cosmic distances, creating a vast network of electromagnetic connections that influenced structure formation far from their sources. These magnetic highways served as conduits for the transport of both energy and information, creating correlations between widely separated regions of space that helped establish the large-scale coherence we observe in cosmic structure today. The interaction between primordial black holes and the dark matter that dominated the universe's mass budget created feedback loops of stunning complexity. Dark matter particles that ventured too close to black hole event horizons would disappear forever, carrying away angular momentum and reducing the spin rates of these cosmic monsters. But the gravitational stirring caused by black hole motion through dark matter halos would heat the surrounding medium, creating expanded regions where structure formation was suppressed while enhancing it in neighboring areas. These dark matter interactions operated through purely gravitational mechanisms, but their effects were profound and long-lasting. The wakes carved by moving primordial black holes through dark matter distributions would have persisted for billions of years, creating preferred directions for subsequent structure formation that might still be detectable in the cosmic web today. The statistical properties of these gravitational wakes encode information about the masses and velocities of primordial black holes, providing potential observational signatures that could be detected through large-scale galaxy surveys. The evaporation of the smallest primordial black holes would have created some of the most spectacular fireworks in cosmic history. As these microscopic monsters reached the final stages of their lives, their surface temperatures would have soared to levels where they emitted not just ordinary particles but exotic forms of matter that existed nowhere else in the universe. The cascade of particles produced in these evaporation events would have included species that decay almost instantly, creating brief moments when tiny volumes of space contained energy densities approaching those of the Big Bang itself. These primordial explosions would have enriched the early universe with high-energy photons and exotic particles that influenced the formation of the first complex structures. The gamma-ray bursts associated with quantum black hole evaporation would have been visible across cosmic distances, creating brief beacons that illuminated the cosmic dark ages with radiation unlike anything produced by conventional astrophysical sources. The neutrinos and gravitational waves generated in these explosions would have carried information about the evaporation process across the universe, creating subtle signatures that might still be detectable in the cosmic microwave background radiation. The information paradox associated with black hole evaporation takes on special significance when applied to primordial objects. If these ancient black holes contained information about the initial conditions of the universe, their complete evaporation would represent an irreversible loss of knowledge about cosmic origins. The quantum correlations between evaporated particles and the information they once contained might persist as subtle entanglement patterns distributed throughout the universe, creating a form of cosmic memory that transcends the individual objects that created it. Recent theoretical developments in holographic physics suggest that the information contained within primordial black holes might not be truly lost, but rather encoded on their event horizon boundaries, in ways that preserve all correlations with the external universe. If this holographic principle applies to primordial objects, their evaporation would not destroy information, but rather redistribute it throughout space in patterns so complex that reconstruction would require knowledge of quantum correlations across cosmic scales. The merger dynamics of primordial black holes operated under conditions that have no modern parallel. When two of these ancient objects spiraled into each other, they would have generated gravitational waves with amplitudes and frequency characteristics that reflected the unique properties of their formation epoch. The space-time ripples produced by these primordial mergers would have propagated through a universe with different expansion rates and matter densities than we observe today, creating wave patterns that carry encoded information about cosmic conditions in the earliest epochs. The numerical simulation of primordial black hole mergers presents computational challenges that push the limits of current technology. The extreme mass ratios and exotic matter configurations involved in these ancient collisions require theoretical frameworks that merge general relativity with quantum field theory in regimes where both become strongly coupled. The resulting calculations must account for effects that range from quantum vacuum polarization to the nonlinear dynamics of curved spacetime, creating models of breathtaking mathematical complexity. But perhaps the most profound aspect of primordial black hole mergers was their role in establishing the causal structure of the early universe. The gravitational wave signals produced by these events would have created correlations between distant regions of space, linking areas that appeared to be completely disconnected through the common influence of propagating space-time curvature. These gravitational connections might have played a crucial role in establishing the large-scale homogeneity and isotropy that characterize our observable universe. The chemical evolution patterns around primordial black holes created unique abundance signatures that might still be observable in the older stellar populations. The nuclear processing that occurred in the extreme radiation fields surrounding these objects would have produced isotopic ratios unlike anything created in conventional stellar nucleosynthesis. The detection of these primordial abundance patterns would provide direct evidence for the existence of early black holes and valuable constraints on the physics of their accretion processes. The search for these chemical fossils requires observational techniques that can probe the composition of stars with ages approaching that of the universe itself. The most metal-poor stars in our galaxy's halo might retain traces of material that was processed in the environments around primordial black holes, carrying within their atmospheres the chemical signatures of cosmic processes that occurred when the universe was still learning the rules of stellar formation. The population synthesis models that describe the evolution of primordial black holes must account for a vast range of physical processes that operated under the extreme conditions of the early universe. These models must incorporate the effects of exotic matter interactions, magnetic field amplification, relativistic jet dynamics, and quantum evaporation processes, all operating simultaneously in environments where the familiar approximations of modern astrophysics break down completely. The observational signatures of surviving primordial black holes present some of the most subtle detection challenges in modern astronomy. Unlike stellar mass black holes that reveal themselves through dramatic accretion events or gravitational wave emissions, primordial objects might exist as nearly invisible gravitational fossils scattered throughout cosmic structure. Their detection requires observational strategies that can identify the subtle gravitational effects of compact objects with masses and spatial distributions that reflect their exotic origins. The gravitational microlensing surveys that search for primordial black holes must distinguish their signatures from those of conventional astrophysical objects while accounting for the complex selection effects that determine which events are detectable. The statistical analysis of these surveys requires sophisticated modeling techniques that can extract the faint signals of primordial objects from the overwhelming background of stellar microlensing events and instrumental noise. Recent advances in machine learning algorithms have opened new possibilities for detecting the subtle patterns that might reveal the presence of primordial black holes in astronomical datasets. These artificial intelligence systems can identify correlations and anomalies in observational data that would be impossible for human analysts to recognize, potentially revealing the hidden signatures of ancient gravitational objects that have remained invisible for billions of years. The theoretical framework that describes primordial black hole formation continues to evolve as new insights emerge from the intersection of cosmology, particle physics, and quantum gravity. The most recent models incorporate effects from string theory, loop quantum gravity, and other candidate theories of quantum spacetime, creating predictions for primordial black hole properties that reflect the deepest levels of physical reality. These advanced theoretical models suggest that the formation of primordial black holes might have been intimately connected to the fundamental phase transitions that shaped the early universe. The breaking of symmetries that separated the fundamental forces might have created conditions where black hole formation became not just possible, but inevitable, ensuring that these objects would emerge as natural consequences of cosmic evolution, rather than rare accidents of extreme density fluctuations. The connection between primordial black holes and the inflationary epoch that preceded the Big Bang nuclear synthesis era remains one of the most active areas of theoretical research. Different models of cosmic inflation predict characteristic patterns in the primordial density, perturbations that would translate into specific mass distributions for the resulting black hole populations. The detection and characterization of surviving primordial black holes could therefore provide direct observational tests of inflationary cosmology and constraints on the physics that operated during the universe's most rapid expansion phase. The role of primordial black holes in establishing the initial conditions for structure formation extends far beyond their direct gravitational effects. These ancient objects would have created preferred locations for the accumulation of dark matter, establishing the seeds around which the first dark matter halos could form. The resulting structure formation process would have proceeded along pathways that were fundamentally different from those predicted by models that ignore primordial black hole contributions. The feedback mechanisms between primordial black hole growth and the formation of the first stars created complex evolutionary sequences that determined the chemical and dynamical properties of the earliest galaxies. Regions where black holes formed early and began accreting efficiently would have been heated by the resulting radiation, creating conditions that favored the formation of massive stars with short lifetimes and explosive deaths. These stellar populations would have enriched their surroundings with heavy elements through supernova explosions, creating the chemical gradients that influenced subsequent generations of star formation. The legacy of primordial black holes extends into the modern universe in ways that continue to shape cosmic evolution. The gravitational potential wells they created billions of years ago still influence the motion of matter on the largest scales, contributing to the cosmic flows that determine how galaxies move through space. The magnetic field structures they established continue to thread through cosmic filaments, providing the seed fields that are amplified by dynamo processes in forming galaxies and clusters. As we drift deeper into this exploration of cosmic origins, we encounter questions that challenge our most fundamental assumptions about the nature of reality itself. The first black holes emerged from a universe so alien, so removed from our direct experience, that they serve as windows into realms of physics that remain largely unexplored. They were born in an epoch when the familiar constants of nature were still settling into their current values, when space and time themselves were more fluid and dynamic than anything we can observe today. The study of these primordial monsters forces us to confront the limits of human knowledge and the boundaries of what can ever be directly observed. Much of their story remains hidden behind event horizons that no signal can ever cross, locked away in regions of space-time where the familiar concepts of past and future lose their meaning. Yet through the subtle traces they left in the cosmic microwave background, through their influence on the large-scale structure of the universe, and through their potential role as components of dark matter, these ancient objects continue to whisper their secrets across the vast expanses of space and time. Tonight, as you prepare to surrender consciousness to the gentle embrace of sleep, remember that you are connected to these cosmic giants through chains of causation that stretch back to the very birth of time itself. The atoms that compose your body were influenced by gravitational fields that were shaped by primordial black holes. The galaxy that contains our solar system, assembled around dark matter structures that bear the fingerprints of these ancient architects. Even the thoughts flowing through your mind as you contemplate these mysteries depend on neural processes that operate according to physical laws that were first explored in the extreme environments around the universe's earliest black holes. The question of what was the first black hole may ultimately teach us something profound about the nature of cosmic evolution itself. These objects were not merely extreme gravitational anomalies, but cosmic pioneers, the first structures to explore the deepest mysteries of existence and to push the boundaries of what matter, energy, space, and time could become under the influence of gravity's patient, inexorable embrace. In their formation and evolution, the universe began its long journey of self-discovery, learning through gravitational collapse and accretion the fundamental principles that would govern the emergence of complexity and beauty across cosmic time. The primordial black holes that formed in the universe's youth were more than astronomical objects. They were cosmic philosophers, using the language of curved space-time to ask questions about the nature of reality that we're only now beginning to understand. Their dark hearts contained laboratories where the most fundamental physics played out under conditions that have never been replicated, creating insights into the workings of the cosmos that remain encoded in their gravitational signatures and the structures they helped create. As you drift towards sleep, carried by the ancient rhythms that connect your biological processes to the cosmic cycles that have unfolded since the universe began, remember that the story of the first black holes is ultimately the story of how the cosmos learned to create regions of such extreme curvature that they became timeless, existing outside the normal flow of cause and effect, as eternal monuments to the universe's capacity for transcending the boundaries of the possible. The gravitational influence of these primordial architects extended far beyond their immediate neighborhoods, creating ripple effects that would cascade through cosmic evolution for billions of years. As the universe continued its relentless expansion, these ancient black holes found themselves embedded in an increasingly complex web of interactions that would shape not just the formation of structure, but the very character of space and time itself. Consider the extraordinary fact that these objects existed in a universe where the very notion of distance was still being negotiated. In the early cosmos, the rapid expansion of space meant that regions which were once in causal contact could suddenly find themselves separated by horizons that no signal could cross. Primordial black holes that formed in close proximity might have been carried apart by cosmic expansion before they could interact, creating a population of isolated gravitational fossils scattered across vast distances. But for those black holes that remained within each other's gravitational influence, the dance of mutual attraction created some of the most complex dynamical systems ever to exist in nature. Binary primordial black holes would have spiraled toward each other through orbits that were constantly shrinking due to the emission of gravitational waves. Their final merger, creating space-time disturbances so powerful that they would have influenced the formation of structure across enormous volumes of space. The energy released in these primordial mergers defies easy comprehension. When two massive black holes finally coalesced, they would have converted a significant fraction of their combined mass into pure gravitational wave energy, creating ripples in space-time that carried more power than the electromagnetic output of billions of galaxies. These waves would have propagated through the early universe at the speed of light, carrying with them information about the extreme physics that governed black hole interactions in conditions that will never be repeated. The detection of these ancient gravitational wave signatures represents one of the holy grails of modern astrophysics. Unlike the relatively nearby black hole mergers that current detectors observe, the signals from primordial coalescences would have been redshifted by billions of years of cosmic expansion, stretching their characteristic frequencies into ranges that require entirely different observational strategies. Future space-based interferometers might be sensitive enough to detect these primordial echoes, opening a new window into the universe's most violent infancy. But the influence of primordial black holes extended beyond the gravitational realm into the electromagnetic spectrum in ways that created some of the first sources of light in cosmic history. As matter fell into these ancient monsters, it would have been accelerated to tremendous velocities, heating to temperatures where it glowed with the brilliance of countless suns. These early quasars would have been visible across cosmic distances, their light traveling for billions of years to illuminate regions of space that had never before experienced electromagnetic radiation. The spectra of these primordial light sources would have been unlike anything we observe in the modern universe. The extreme magnetic fields and radiation densities around accreting black holes would have created conditions where photons interacted with matter in regimes that pushed quantum electrodynamics to its limits. The resulting emission would have exhibited spectral features that have no analogue in contemporary astrophysical sources, carrying signatures of physical processes that operated only in the universe's earliest epochs. The reionization of the cosmic medium by these early quasars marked a fundamental phase transition in the universe's evolution. The intense ultraviolet radiation from accreting primordial black holes would have stripped electrons from hydrogen atoms across vast volumes of space, transforming the neutral gas that filled the cosmos back into a plasma state. This process would have created bubbles of ionized material around each bright source, bubbles that gradually expanded and merged until the entire universe had undergone this cosmic phase change. The topology of reionization created by primordial black holes would have been fundamentally different from that produced by the first stars. While stellar sources created relatively small ionization bubbles that grew slowly as more stars formed, the much more luminous primordial quasars would have created enormous ionized regions almost instantaneously. The resulting reionization pattern would have been highly inhomogeneous, with some regions becoming ionized very early while others remained neutral for much longer periods. This patchy reionization would have had profound consequences for subsequent structure formation. Ionized regions would have experienced different thermal evolution than neutral areas, leading to variations in the gene's mass that determines the characteristic scale of gravitational collapse. The resulting structure formation process would have been highly nonlinear, with feedback effects that coupled the growth of primordial black holes to the formation of the first stars and galaxies in complex ways that we are only beginning to understand. The chemical enrichment patterns created by primordial black hole activity would have been unlike anything produced by conventional stellar processes. The extreme radiation fields surrounding these objects would have triggered nuclear reactions in the surrounding gas that created isotopic ratios with no modern analogue. Elements that are typically produced only in stellar cores or supernova explosions might have been synthesized through entirely different pathways in the intense environments around accreting black holes. The detection of these primordial abundance patterns in the oldest stellar populations would provide smoking gun evidence for the existence of early black holes. Astronomers are beginning to develop the observational techniques necessary to probe the composition of stars with ages approaching that of the universe itself, searching for the chemical fossils that might reveal the influence of these ancient gravitational giants. The magnetic field generation around primordial black holes created some of the first large-scale magnetic structures in the universe. The dynamo processes operating in their accretion disks would have amplified weak seed fields to strengths that exceeded anything achievable through conventional astrophysical mechanisms. These primordial magnetic fields would have extended far beyond the black holes themselves, threading through the surrounding medium and influencing the formation of structure across cosmic scales. The interaction between these magnetic fields and the flow of matter created complex magnetohydrodynamic phenomena that shaped the early universe in ways that remain poorly understood. magnetic reconnection events in the twisted field lines around primordial black holes would have released enormous amounts of energy, creating shock waves and particle acceleration processes that influence the thermal and chemical evolution of surrounding gas clouds. The legacy of these primordial magnetic fields extends into the modern universe, where they might serve as the seed fields that are amplified by galactic dynamos to create the magnetic structures we observe in contemporary galaxies and clusters. The statistical properties of these fields would carry information about the distribution and properties of primordial black holes, providing potential observational signatures that could be detected through careful studies of cosmic magnetism. The formation of the first cosmic structures around primordial black holes created environments that were fundamentally different from those predicted by standard models of structure formation. The deep gravitational potential wells created by these massive objects would have attracted surrounding dark matter, creating dense halos that could trap and accumulate ordinary matter much more efficiently than conventional dark matter fluctuations. These enhanced accretion processes would have led to the rapid assembly of the first proto-galaxies around primordial black hole seeds. The resulting objects would have been more massive and more tightly bound than galaxies that formed through conventional hierarchical clustering, creating a population of early structures with properties that might still be observable in the most distant regions of the universe accessible to our telescopes. The feedback between primordial black hole growth and early galaxy formation created evolutionary pathways that determine not just the masses and structures of individual galaxies, but also their clustering properties on larger scales. Regions where multiple primordial black holes formed in close proximity would have experienced enhanced structure formation, creating the seeds of the massive galaxy clusters we observe today. Other areas where primordial black hole formation was suppressed would have evolved more slowly, creating the cosmic voids that punctuate the large-scale structure of the universe. The observational signatures of this enhanced structure formation might be detectable through careful studies of the cosmic microwave background radiation and large-scale galaxy surveys. The statistical properties of structure on different scales would carry information about the contribution of primordial black holes to early cosmic evolution, providing tests of theoretical models that could distinguish between different formation scenarios. The quantum properties of the smallest primordial black holes created connections between the microscopic and macroscopic worlds that operated through purely gravitational mechanisms. These tiny objects would have existed at the intersection of quantum mechanics and general relativity, their behavior governed by physics that we can describe mathematically, but struggle to understand conceptually. The Hawking radiation emitted by quantum-sized primordial black holes would have carried information about the quantum states of matter under extreme curvature conditions. The entanglement patterns between particles inside and outside the event horizon would have created correlations that extended across cosmic distances, linking regions of space that appeared to be completely disconnected through the subtle quantum connections mediated by black hole physics. These quantum correlations might have played a crucial role in establishing the large-scale coherence properties of the universe. The entanglement between particles that fell into primordial black holes and those that remained in the surrounding medium could have created the initial conditions necessary for the subsequent evolution of cosmic structure, ensuring that widely separated regions of space maintain the correlations necessary for the formation of the cosmic web. The evaporation signatures of these quantum black holes would have created brief moments when tiny volumes of space experienced conditions that rivaled those of the Big Bang itself. The cascade of exotic particles produced in these micro-explosions would have enriched the early universe with forms of matter and energy that existed nowhere else in nature, creating unique chemical and physical conditions that influence the formation of the first complex structures. The search for these evaporation signatures in the cosmic microwave background represents one of the most challenging observational programs in modern cosmology. The statistical analysis of temperature and polarization fluctuations must account for a vast range of systematic effects, while searching for the incredibly subtle signals that might reveal the explosive deaths of primordial quantum black holes that occurred when the universe was still in its infancy. The theoretical framework that describes primordial black hole evaporation must incorporate effects from quantum field theory in curved spacetime, statistical mechanics of black hole thermodynamics, and the cosmological evolution of the background universe. The resulting calculations push the boundaries of our computational capabilities while revealing deep connections between apparently disparate areas of theoretical physics. The information paradox associated with primordial black hole evaporation takes on cosmic significance when we consider that these objects might have contained information about the initial conditions of the universe itself. If primordial black holes formed from specific patterns in the primordial density field, their complete evaporation would represent an irreversible loss of information about cosmic origins that challenges our understanding of the fundamental nature of physical information. Recent developments in holographic physics suggest that this information might not be truly lost, but rather encoded in subtle correlations between the evaporation products and the structure of spacetime itself. The holographic principle implies that all information about the interior of a black hole is encoded on its event horizon boundary, suggesting that primordial black hole evaporation might redistribute this information throughout the universe in patterns so complex that reconstruction would require knowledge of quantum correlations across cosmic scales. The implications of this holographic encoding extend far beyond the fate of individual black holes to encompass questions about the fundamental nature of spacetime and information. If the universe itself can be understood as a holographic projection of information encoded on cosmic horizons, then primordial black holes might have played a crucial role in establishing the information-theoretic foundations of physical reality. As we continue our gentle exploration of these cosmic mysteries, we find ourselves drawn into questions that touch the deepest foundations of existence itself. The first black holes emerge from conditions so extreme, so removed from our everyday experience, that they serve as windows into realms of physics that remain largely unexplored. They were born in an epoch when the familiar laws of nature were still crystallizing from more fundamental principles, when the very concepts of space, time, matter, and energy were taking their first tentative steps toward the forms we recognize today. The study of these primordial giants forces us to confront the limits of human knowledge and the boundaries of what can ever be directly observed. Much of their story remains hidden behind event horizons that no signal can cross, locked away in regions of spacetime where our most sophisticated theories dissolve into mathematical singularities. Yet through their gravitational influence on cosmic structure, through their role in reionizing the universe, and through their potential contribution to dark matter, These ancient objects continue to shape the cosmos in ways that we are only beginning to appreciate. The search for primordial black holes represents more than an astronomical quest. It is a journey into the deepest mysteries of existence, an attempt to understand how the universe learned to create objects so extreme that they transcend the ordinary boundaries of space and time. In their dark hearts, the cosmos first explored the ultimate limits of density and curvature, creating regions where the familiar concepts of past and future lose their meaning, and where the very notion of causality becomes fluid and uncertain. Tonight, as you drift toward the peaceful embrace of sleep, remember that you are part of a story that began with these cosmic pioneers. The elements that compose your body were influenced by gravitational fields, shaped by primordial black holes. The galaxy that shelters our solar system, assembled around dark matter structures that bear their ancient fingerprints. Even the neural processes that generate your thoughts operate according to physical principles that were first explored in the extreme environments of the universe's earliest gravitational monsters. The question of what was the first black hole ultimately leads us to a profound recognition about the nature of cosmic evolution itself. These objects were not merely astronomical curiosities, but cosmic philosophers, using the language of curved space-time to explore the deepest questions about reality. Through their formation and evolution, the universe began its long journey of self-discovery, learning through gravitational collapse and accretion the fundamental principles that would govern the emergence of complexity and consciousness across billions of years of cosmic time. The story of primordial black holes becomes even more profound when we consider their role as cosmic time capsules, preserving within their gravitational embrace information about the universe when it was utterly alien to anything we could recognize today. These ancient objects formed in epochs where the very fabric of reality operated according to rules that challenge our deepest intuitions about existence itself. Picture the universe in those first crucial moments, when temperatures soared to levels where the distinction between matter and energy became meaningless, where particles existed in states of such extreme excitation that they had no stable analogue in our modern cosmos. The primordial black holes that emerged from this cosmic crucible were born not just from matter, but from the raw potential of existence itself, crystallizing from quantum fluctuations that had been stretched to macroscopic scales by the universe's violent expansion. The formation mechanisms available in those ancient times operated through channels that are completely closed off in our contemporary universe. Imagine regions where the energy density was so extreme that space itself became unstable, where quantum fields underwent phase transitions that created pockets of false vacuum decay, where the very geometry of space-time folded back upon itself in configurations that defied our understanding of dimensional structure. Some primordial black holes might have formed through the collision of cosmic defects, one-dimensional strings of pure energy that stretched across distances larger than our observable universe today. When these cosmic strings intersected, they would have created knots of concentrated energy so dense that gravitational collapse became inevitable, birthing black holes with properties that reflected their exotic stringy origins. Others might have crystallized around magnetic monopoles, hypothetical particles that carried isolated magnetic charges, unlike anything observed in nature. These monopole black holes would have possessed electromagnetic properties that transcended our familiar understanding of charged objects. their event horizons threaded with magnetic field lines of impossible intensity that created regions where electromagnetism and gravity merged into a unified field phenomenon. The diversity of these formation pathways created a zoo of primordial black holes with characteristics that defy our modern classification schemes. Some were born with intrinsic rotation rates that approached the theoretical maximum allowed by general relativity, their ergospheres extending far beyond their event horizons to create regions where space-time itself was dragged into a cosmic whirlpool of such intensity that the very notion of stationary reference frames became meaningless. The accretion processes around these rapidly spinning objects operated through mechanisms that have no contemporary parallel. Matter falling into their gravitational wells would have been subjected to frame-dragging effects so severe that it experienced temporal and spatial distortions that challenged the fundamental assumptions of thermodynamics. The resulting accretion disks would have exhibited properties that pushed plasma physics into regimes where our current theories reach their absolute limits. The magnetic field generation in these primordial accretion systems created dynamo processes of unprecedented efficiency. Weak seed fields were amplified through magneto-rotational instabilities that operated under conditions where the distinction between magnetic and gravitational effects became blurred. The resulting field configurations would have extended across cosmic distances, creating a vast web of electromagnetic connections that influenced the formation of structure throughout the early universe. These magnetic networks served as invisible highways for the transport of energy and angular momentum, creating correlations between widely separated regions of space that helped establish the large-scale coherence we observe in cosmic structure today. The statistical properties of these primordial magnetic fields would have been unlike anything produced by conventional dynamo mechanisms, exhibiting scaling laws and correlation functions that reflected their exotic origins in the extreme physics of rapidly rotating black holes. The gravitational wave signatures produced by these spinning primordial objects would have been equally exotic. Unlike the relatively simple chirp patterns generated by modern black hole mergers, the coalescence of primordial black holes would have created complex waveforms that encoded information about their unique formation histories and internal structures. These ancient gravitational melodies might still be echoing through the cosmos, redshifted by billions of years of expansion into frequency ranges that require entirely new detection strategies. The search for these primordial gravitational wave fossils represents one of the most ambitious observational programs ever conceived. Future space-based interferometers with arm lengths measured in millions of kilometers might be sensitive enough to detect these ancient signals, opening a new window into the universe's most violent infancy and revealing the properties of black holes that formed under conditions that will never be replicated. But perhaps the most remarkable aspect of primordial black holes was their role in establishing the causal structure of the early universe. These objects served as gravitational lighthouses, their intense fields creating preferred directions for the flow of matter and energy that would influence cosmic evolution for billions of years to come. The space-time curvature around each black hole created a local coordinate system that helped define the geometric relationships between different regions of space. The interaction between multiple primordial black holes created gravitational interference patterns of stunning complexity. When their fields overlapped, they generated standing waves in the curvature of space-time itself, creating regions where gravitational focusing effects were enhanced while suppressing them elsewhere. These interference patterns served as templates for subsequent structure formation, establishing the filamentary architecture that characterizes the cosmic web we observe today. The quantum mechanical properties of these gravitational interference patterns operated at the intersection of general relativity and quantum field theory, creating correlations between widely separated regions through purely gravitational mechanisms. The entanglement patterns generated by these interactions might have established the initial conditions necessary for the subsequent evolution of cosmic structure, ensuring that the universe maintained its large-scale homogeneity while developing the small-scale inhomogeneities that would eventually grow into galaxies and stars. The evaporation of the smallest primordial black holes created brief moments when the universe experienced conditions that rivaled those of its own birth. As these quantum-sized objects reached the final stages of their lives, they would have emitted cascades of exotic particles that existed nowhere else in nature, creating unique chemical and physical environments that influence the formation of the first complex structures. The particle species produced in these primordial explosions would have included forms of matter that have no stable existence in our current universe. Particles with masses and interaction strengths that reflected the extreme physics of black hole thermodynamics. The decay products of these exotic particles would have enriched the early cosmos with high-energy radiation and rare isotopes that influence the nuclear processes occurring in the first stellar cores. The detection of these primordial abundant signatures in the oldest stellar populations would provide direct evidence for the existence of quantum black holes in the early universe. Astronomers are developing increasingly sophisticated spectroscopic techniques to probe the chemical composition of stars, with ages approaching that of the cosmos itself, searching for the isotopic fingerprints that might reveal the influence of primordial black hole evaporation on early nucleosynthesis processes. The theoretical framework that describes these evaporation processes must incorporate effects from quantum field theory in curved spacetime, the thermodynamics of black hole horizons, and the cosmological evolution of the background universe. The resulting calculations reveal deep connections between apparently disparate areas of physics, showing how the quantum properties of microscopic black holes influence the macroscopic evolution of cosmic structure. The information theoretic implications of primordial black hole evaporation extend far beyond the fate of individual objects to encompass fundamental questions about the nature of physical information itself. If these ancient objects contained encoded information about the initial conditions of the universe, their complete evaporation would represent either an irreversible loss of cosmic memory or a redistribution of this information into patterns so subtle that reconstruction would require knowledge of quantum correlations across cosmological scales. Recent developments in holographic physics suggest that the information contained within evaporating black holes might be preserved in the entanglement patterns between their Hawking radiation and the quantum vacuum fluctuations of empty space. This holographic encoding would create a form of distributed cosmic memory that transcends individual objects, storing the history of the universe's birth in the correlation functions of quantum fields that fill all of space-time. The implications of this holographic information storage extend into the realm of cosmic consciousness, suggesting that the universe itself might possess a form of memory that emerges from the collective behavior of quantum correlations established by primordial black hole evaporation. This cosmic memory would be encoded not in any particular location, but in the statistical properties of quantum entanglement that permeates the fabric of reality itself. The search for these information-theoretic signatures represents one of the deepest challenges in modern theoretical physics. The detection of holographic information patterns would require observational techniques that could probe the quantum correlations between widely separated regions of space, revealing the hidden connections that link the microscopic and macroscopic scales of cosmic structure. As we drift deeper into this exploration of primordial mysteries, we encounter questions that transcend the boundaries of conventional physics and venture into realms where science meets philosophy in contemplation of existence itself. The first black holes were not merely gravitational anomalies, but cosmic pioneers that explored the deepest wells of space-time curvature, creating regions where the familiar concepts of space and time dissolved into something far more fundamental and mysterious. And so we reach the end of our gentle journey through the deepest cosmic mystery of all, having traced the story of the universe's first black holes from their birth in the quantum foam of creation to their lasting influence on the cosmos we observe today. These primordial giants were more than astronomical objects. They were the universe's first philosophers, using the language of curved space-time to ask questions about existence that we are only now beginning to understand. Tonight, as you drift towards sleep, remember that you carry within your very atoms the legacy of these ancient architects, and that their story continues to unfold in every star that shines, every galaxy that turns, and every moment of cosmic time that passes in this beautiful, mysterious universe we call home.